the introduction to the Laplace transform. Okay, it's a machine. So it's a machine. Each machine is going to be a function. This is going to be the case. So this is going to be Laplace. Okay, Laplace transform. Transformation or just Laplace transform. You know that great French mathematician, Laplace. Some people, they pronounce this one Laplace, but the French one is Laplace. That's going to be the one. So I'm going to refer to it as a Laplace. Okay, so we can call it Laplace if you like. Okay, now, in order to do it, we should remind you that we are going to use quite a lot of the improper integrals. So we recall what we need for the improper integral from calculus. Okay, calculus 2 first. So we recall. Okay, recall that if you have a function, okay, if g is going to be a function, a continuous function mostly, or otherwise, recall that if g is a function, okay, for example, defined, I just get the range that we are interested in, or the domain that's going to be. G is a function defined on this interval, 0 and positive infinity, then the improper integral, okay, the improper integral 0 to positive infinity of g of t, d of t, okay, is going to be defined, by, you know that it's improper because of infinity. You can define the integral on a closed interval. And this is not. Okay, it's going to be defined by what? We replace the infinity by t or another things that you like. So it's going to be 0 to positive infinity, g of t, d of t. We replace the infinity by something like, b, c, d, and then we take the limit. Okay, it's going to be limit of t goes to positive infinity, integral of, that's going to be 0, replace infinity by anything you like. I replace it by b, g of t, d of t. Okay, integral from 0 to b, g of t dt is proper integral. You just use any formula, when you find it, the result is going to be, okay, sorry, this must be b goes to positive infinity. Okay, the result of an integral is going to be a function of b. Since the function of b, you take the limits. You may have to use different methods from the limit. Most of the time, you may have to use the L'Hopital rule to find out if the limit does exist. If the limit exists, the answer is the solution to the integral, and we say that the integral converges. If the limit does not exist, most of the time it's going to be infinity. In that case, we say that the integral is divergent. Okay, divergent and convergent. Of course, we are going to be interested in the convergent part. Okay, so if the limits, okay, if that limit exists, then the improper integral, the integral from 0 to positive infinity, g of t, d of t, okay, converges. Otherwise, okay, otherwise the integral diverges. Okay, the integral diverges. So it depends on the function. You may get a convergent or you may get a divergent. You get these numbers. Okay, quickly give you one example just to remind you how we're going to do it. So for example, we want to evaluate this integral. Okay, integral from 0 to positive infinity. And this will do something like 1 over 2x plus 1 dx. Okay. So just apply the definition, change the infinity into the something like b, t, doesn't matter. Okay, so the solution is going to be integral from 0 to positive infinity, 1 over 2x plus 1. Let's call it 2x plus 1 square. I want something to be convergent. Okay, this is the one. So it's going to be limit of, for example, b goes to positive infinity, integral from 0 to b. Okay, 1 over 2x plus 1 whole squared dx. Now we're going to take the integral inside the limits. Okay, you know that. You move it up and use the power rule. So it's going to be equal to, okay. So it's going to be equal to the limit of b goes to positive infinity. Rewrite it 0 to b, and that would be 2x plus 1 to the negative 2 dx. You want to find this integral. If you take the inside to be u, your prime would be 2. So I needed 2. So what I do is I divide the outside by 2. Okay. And then I multiply the inside by 2. So 2 times 2x plus 1 to the negative 2 dx. So I have the u du. So this is going to be like the integral of u to the negative 2 du. And you operate it. So it's going to be equal to the 1/2. Okay. It's going to be equal to the 1/2 u to the negative 1. So it's going to be the limit of b goes to positive infinity. So this would be 2x plus 1 to the negative 1/2 over negative 1, and to be evaluated from 0 to b. You switch this one into a positive power, and then you take the limits. Limit of b goes to positive infinity. Okay, so we're going to have a negative 1 over 2x plus 1, integral going from 0 to b. Substitute. So it's going to be 1/2. The limit of b goes to positive infinity. If you substitute the b for x, so that give you negative 1 over 2b plus 1. But if you substitute for 0, so that give you negative 1 over 0 plus 1. And then when you're done, you take the limit when b goes to positive infinity. When b goes to positive infinity, the numerator would be infinity. So this fraction would be 0. And this is simply negative, positive. So the result would be 1/2 times 1, which is 1/2. So the original integral, 0 to infinity, 1 over 2x plus 1, okay, all squared dx is equal to the 1/2. And the integral, of course, is convergent. Okay, so this is the way we're going to do it. We are going to do this one quite a lot in this, okay, in this chapter. Sometimes, if you don't like to keep the limits, you can do the integral, simplify it, then go back and take the limit. Yes. No, you can take it out. That was kind of easy, so I just keep it. But you can do the limit, but you have to come back and take the limits. Okay. Any question? Now we are ready to give you the definition of the Laplace transform. The Laplace transform would be a tool, okay, that we're going to apply to any function. Okay, so let's introduce the Laplace transform. Okay, there are some other theorems from the calculus too that, we don't need much of them. There are a couple of them I'm going to refer to it at the end. Okay, so let's go to the definition of the Laplace transform. Now, for this one, a function would be given to you, operate this operator on the function. So what is the definition of the Laplace transform? Definition. Suppose you be given a function, okay? Laplace transform is going to be a kind of operator. The operator is like a function. So what we are going to do, we are going to give a given function. We drop it into this machine that we are going to introduce. The function is going to be a function of t because it's application problem. So we're referring to the time. So let's say this is going to be a function. Okay, let's say a function f of t. You drop it into the Laplace machine. This is it. The Laplace machine notation is L of f of t. Okay, this is the way I write the L. Okay, for the Laplace. So we can change it if you like, but I stay with this one because we want to show it's something different. So we got the function f of t. We drop it into the Laplace machine. Now what's going to be the Laplace machine? Yes?
It's that symbol.
L for Laplace. If you don't like it, L of f of t. But we make it a special. This L would refer to the Laplace. So if you see this one anywhere else, you know that we talk about the Laplace transform. Okay, so we drop the function into the Laplace machine. So what's going to be the output? The Laplace is, this is the Laplace formula. The Laplace of f of t is going to be an improper integral. The integral is 0 to positive infinity e to the negative st. That's a lowercase s that we're going to use. E to the negative st f of t d of t. That would be the definition of the Laplace transform. Okay, so you drop the function. It's like the other operation that you're going to have, differentiation. Differentiation is an operator. You drop the function into the derivative machine. You see, if you drop the x to the fifth to the derivative machine, the result will be 5x to the fourth. But this is the way we're going to define the Laplace transform. As you can see, this is going to be improper integral. So if this improper integral is going to be convergent, then you are going to get your result. Let's see what type of function is this one. You see, f of t is going to be a function of t. When you integrate over here, you integrate respect to the t. There is a s here. So when you substitute, you do all the operation, the result would be a function. A function of what? No. T would disappear. The function of s. Okay, so this is going to be a function of the function of s. So officially, this is how we're going to define it. So your function must be a nice one. So at least it must define between 0 and positive infinity. Okay, so the official definition is this one. If you give me a function, if a function, okay, if a function f is defined, okay, is defined on this interval. The interval must be 0 and positive infinity. It may be defined all over the places, but you want to make sure that it's defined in this interval that you want to indicate, okay? If it's going to be defined in this interval, then the Laplace transform, okay? The Laplace transform. Laplace transform of this function of f is denoted by notation L of f of t. That's a notation. And it's going to be defined and is defined by this formula. The formula is Laplace of f of t. I just repeat that formula at the top. 0 to positive infinity. E to the negative st ft dt. Okay. Of course, if this integral converges, you get the numbers. Now, the thing that you have to consider is this one. Note that this function, L of f of t, is a function of s. Is a function of the variable s. Okay, so the way we write it, these are standard notation that we're going to use through this chapter. So we write L of f of t. It's denoted by f of s. That's it. So in this chapter, anytime you see the f of s, you know what you are talking about. You're talking about the Laplace of f of t. Yes.
So the example you gave at the beginning, is that like the first step we would take, and then we would plug it into this?
Yeah, that example, the function was, there was no e to the negative st. Yeah, you just do the 0 to infinity, but your function is going to be more involved because of that. I just want to remind you the action. And we're going to do the same action over here, but you do it for the proper function, the special function. The function will be given to you, you want to have the Laplace, you form this improper integral, so you have to do the improper integral, okay? That give you the result. Now, the important part is this one. The Laplace transform is a function, but it's a function of s. So this function of s, s must have a domain of the function. So what's going to be the domain of this function? Okay, the domain of this function means what? Means the proper s that you can use. So where s is coming from? S is coming from here, inside improper integral. You can have the s if this integral exists. This integral exists if the integral is convergent. So the domain of the Laplace transform function f of s is the same as the conditions that you may have to impose on s so that this integral is going to be convergent. Okay, and it's very important case for us to know this one. Okay, so this is going to be the function, then the domain of this function of f of s is going to be what? Is the set of all values of s for which the improper integral, okay, the improper integral, that improper integral repeated, 0 to infinity, e to the negative st, ft dt converges. So you will see it in a minute that when you want to apply the Laplace transform, always at the end, it's going to be involved s. So it's very convenient for you. You impose any condition that make it into the convergence. So you cannot predict it at the beginning. You will see it through the action that you're going to have. Yes.
In the notation for your Laplace transform, you be changing it from either positive infinity or just infinity?
It doesn't matter. When I use infinity here, it's always possible. Okay. Sometimes they do. Okay. Any question? Make sure you have a good idea of this function, the definition, the beginning, because you are going to operate with this one over and over and over. Yes.
Does that mean you just need the same domain before?
No. No, you see, when you take this, you will see it in a minute. When you operate this integral, there are two possibilities. The integral can be convergent or can be divergent. You are not interested in divergence. You are interested in convergent all the time. So it's up to you. We force it to be convergent. How are we going to do it? We force the condition on s. So automatically we get the convergent. If there is any condition, we say, okay, the domain of this function is this, s bigger than 2. This is the way, we are going to operate this. So that's going to be fun. Okay, and there you are. Any question? Let's see how we're going to do it. We do a couple of them to get an idea. Of course, it's not easy operation. It's going to be long operation if you want to do it all the time. So what we're going to do, there are a group of famous ones. Okay, that group of famous one, there's going to be a table. You memorize it, you bring the table to the test, and then you'll be done. But there are some in application that maybe it's not going to be consistent with your table. So especially in application problems, you know that all the functions in application problems are piecewise defined functions. When it's a piecewise defined function, it's not just a kind of harmonic function there. It's not sine cosine. So you should be ready for it. That's why we just apply a couple of examples. Then we are going to make it so much easy, if you like, so that we have all the possibilities. But you got to be alert, if you like, to be able to find it. It's not the case that I memorized I memorized the formula, I don't need it. No, I promise you that you are going to need a couple of times to operate it for us, okay? So let's operate a couple of them to see how we're going to do it. Then we give you the table, and then we start it off, okay? So good, very good idea. Get idea of the result. It's a function of S, okay? So it's like a differentiation. Let's start with a function. What's the easiest function to operate? No, a function. What's easiest function that you can have other than zero? What? A constant. Very good. Excellent. So we do the constant first. That's it. Yeah. It's like what? It's like differentiation. So example one. That's it. We want to find the Laplace transform of the following. Just do a couple of them, then I give you the formula for all of them. Find the Laplace transform. Laplace transform. Okay, of each function. Each function. They give you different notation. Sometimes most of the time, the notation is going to be in this form. So the first one, we want to find the Laplace of a constant. In order to get a constant, you need to do only one. If you do the one, the 5 is like 1. Okay, there you are. So your function is your function is 1. Write the definition. Remember the definition, solution. Just remind you the definition here. We keep it for all the problems. Laplace of f of t is 0 to infinity e to the negative st ft dt. So in this case, your f of t is equal to 1. Substitute. So Laplace of 1 is 0 to infinity. If we replace f of t by 1, that gives simply e to the negative st dt, because the function is 1. So start integrating. Change it into the proper one. Limit of b goes to positive infinity. Integral of 0 to b e to the negative st dt. Integrate. It's easy to integrate. Limit of b goes to positive infinity. You know that the exponential function never change, but u prime, you see what's going to be u prime for this one? Derivative with respect to the x. Derivative with respect to the t. Negative s. Negative s is going to be derivative with respect to the t. So it's going to be exponential function. Is exponential function since you integrating divided by negative s. When you differentiate, you multiply by u prime. When you integrate it, you divide. Okay, but going from 0 to b. So continue. You bring it down. Limit of b goes to positive infinity. You write this one as a negative 1 over s e to the st. Then going from 0 to b. Substitute is the limit of b goes to positive infinity. Substitute minus, remember, you replace the t by b. S e to the sb minus, replace the t by 0. 1 over okay, s e to the 0. Okay, so what's going to be the result? When b goes to positive infinity, how about this one over here? What is this limit?
So,
How do you know that it's 0?
because e to the power of infinity would be infinity and one of infinity is 0.
Very good. How do you know it's going to be e to the positive infinity?
Because e to the s b.
Yes, how do you know it's going to be positive?
So it's gonna be
It's easy. We impose the condition. You see,
Oh.
remember, as soon as we need the condition, we impose the condition on S that give us the desired result. So the desired result would be if you can keep this e to the st down the denominator, this would be 0. It would be down the denominator if s is positive. So we say, oh, this goes to 0. I need s to be greater than 0. You see, that's why I was talking about finding the domain of the Laplace transform. Okay, this goes to 0 if s is positive. And in this case, e to the 0 is 1. So this is going to be equal to what? Is equal to the first one is going to be 0 and plus 1 over s. Because e to the 0 is 1. So what's going to be the conclusion? 1 over s. So the conclusion is Laplace transform of 1. Okay, Laplace of 1 would be simply 1 over s with the condition that s must be positive. Okay, that's it. So that's why I'm talking about it. I said that, you impose the condition as you need it. If you don't need any condition, you say for all s. But in this case, you need that condition. Otherwise, this integral is not going to be convergent. It's going to be convergent if you can pick the e to the s down the denominator. B is positive number because b goes to positive infinity. And s is. So this is your first formula. Laplace transform of 1 is 1 over s. Use it over and over and over. Any question? So that's it, the first one. Wait for a second, but
So
yes,
what
question.
if we did define s as negative? Wouldn't we get a completely different answer?
Why we should impose the s to be negative?
What if we just wanted it to be negative? Or what
No,
if-
no, you see, what's the purpose? The purpose is finding the Laplace transform. You can find the Laplace transform if this integral is convergent.
Oh,
This integral is convergent if s is positive.
if not, it wouldn't be converted. Okay.
That's it, yes.
Can you explain, imposing the conditions again?
You see, you want this limit to exist, okay? Your difficulty is this part. When p goes to infinity, if the denominator would be infinity, you get 1 over the infinity, we should say. If this e on the top, if this power happened to be negative, so what would happen there? That e would jump up to the top. As soon as you get to the top, you get the infinity on the top, which is very bad. Okay, remember we are looking for a positive answer. So we make it positive. It's up to us, okay, together. Laplace 1 over s. In application, you use it all the time. Laplace 1 over s. Okay, when it's a formula. But if you want to find it, this is the way. Okay, let's get the next one. The next one is very popular. We're going to use quite a lot, and there is a formula for it. Let's find it, and I'll give you the table. And for your next quiz, we are going to give you a couple of them to find, okay? Because we want to practice. So although you have the formulas, that you may have to prove it for us, okay? So be ready for it. So what's going to be the next one? Next one is exponential function. How about you want to find the Laplace of e to the negative 3t. Exponential function, you want to find the Laplace transform of this exponential function. Okay, set up the formula again. Solution. So your f of t is what? E to the negative 3t. Go to the formula. Laplace of e to the negative 3t is equal to 0 to infinity, e to the negative st times your function. Your function is e to the negative 3t and the dt. Okay, I just use the formula. Then e to the negative st, e to the negative 3t, you know that the base are the same, so you add the top. So it's going to be 0 to infinity. If you add them together, the top would be what? E to the negative st minus 3t dt. Okay. You can also factor out the t if you like it, or you can do it later on. Change it to the formula. Okay, I'm going to change it here before I going in. So what I do is I factor out the t on the top, or a negative t. If I factor out the negative t, the inside is going to be s plus 3 dt. Okay. Now change it to the limit and integrate it. So it's going to be equal to the limit. B goes to positive infinity. Integral from 0 to b. Function e to the negative t times s plus 3 dt. Okay, easy to integrate. Exponential function. Exponential function never change. You get the same one, but you have to divide by u prime. What's your prime here? S plus 3 or negative s plus 3. So it's going to be equal to the limit of b goes to positive infinity. Exponential function as is e to the negative t s plus 3 divided by u prime negative s plus 3. Okay, it's going to be evaluated from 0 to b, and then b goes to positive infinity. U prime. You see, exponential function. When you differentiate exponential function, is exponential function times u prime. Derivative of the top. Derivative of the top is what? Is negative s plus 3. When you do the exponential function, what's the integral of e to the at dt? No, over a u prime. Derivative of the exponent. A, yeah, a. This is the same thing. So your a is s plus 3. Because you differentiate respect to the t. Okay, continue. You are going to replace t by b and the t by 0, and then try to make it into conversion. Okay, so you can bring it down, do it, or just do it, just continue. Okay, so replace it by b first and the 0. I go to the next page and continue. Okay, so it's going to be equal to limit of b goes to positive infinity. If you do the first one, it's going to be e to the negative b times s plus 3 over negative s plus 3. That's the first one. Minus, if you do the 0, the top would be e to the 0. The bottom one would be negative s plus 3. Okay. So I just substitute. Yes.
So for you, have the negative power, wouldn't you put it?
You do it now. Okay, you can do it now. So now we do it now. Because now we have to make a judgment. Okay, so let's do it. Yes, we bring this one down. So it's going to be limit of b goes to positive infinity. So we make the top to be 1. The bottom one would be negative s plus 3 e to the b times s plus 3. What is going to be here? Negative would be positive. And e to the 0 is 1. Yes, that's question.
Wouldn't the s plus 3 go to the top right to be dividing?
No. Why on the top?
If you have 1 over something, and then you're dividing that by something.
No. You don't divide it, you just bring the top down. You have to keep that one as is.
Even if it's zero and one, right?
What's that? Of course, very good.
Why did it go to zero then?
Is one. It's a misprint. Okay, so it's gonna be negative, negative, positive. Just want to see if you follow me. It's gonna be 1 over s plus 3. That's it. Now the judgment. So what you need to do to make sure that this is convergent. The second part is the number. So you have to prepare the first part. Again, you have to keep this e to the b times s plus 3 down the denominator. Because you need that infinity to make this one 0. You are going to have it down the denominator if the power is positive. B is already positive. So what's the condition that we need? S plus 3 must be positive. This means S must be greater than negative 3. So this goes to 0. If what? S plus 3 is positive, which is the same as S to be bigger than negative 3. You see, this is the way you impose the condition. In that case, the result would be nice. 1 over S plus 3. So we arrive at a very important formula. The Laplace of e to the 3t is going to be 1 over s plus 3, with the condition that s must be greater than negative 3. Yes,
So if S is, let's say, 1, we're gonna have e to the b times 4, right? And then you're gonna be having e to the infinity as
Yeah.
the denominator, but then it's gonna be multiplied by a negative.
no,
Is it
as soon as we get e to the infinity, we find. Because e to the infinity would be 0. I mean, over here, e to the infinity would be infinity.
Yeah.
That fraction would be 0. It doesn't matter whatever you have.
But isn't negative infinity, what if I make that?
We don't have negative infinity. You see, we assume that s plus 3 is positive.
Yeah, but we have. a
B is
negative
also
on-
positive.
We have a negative on the outside though.
So doesn't matter.
Okay,
Because it would be 0. Negative 0, 0.
oh, yeah,
That's the one. Okay.
okay.
So let's make, yes.
Why is the condition S plus 3 is greater than 0 and S plus 3 is not known? Why is it greater than 0?
When s is bigger than negative 3, then the denominator would be also not 0.
Yeah, I'm saying like why can't you do greater than 0?
Because in that case, this limit would be infinite. You see, you have to impose the condition to get rid of that domain, that limits. Okay, as long as you keep the e to the whatever down the denominator, you have the infinity. It's a problem. You get the number on the top, infinity on the bottom, 0 right away. Okay, so I just did this one to believe that in general, this is the second formula. Very important formula that you have to memorize this one. Laplace of e to the, okay, Laplace of e to the at. What is the formula for this one? If you compare it with whatever you did. 1 over s y plus
Oh, minus, right?
minus, because I changed it, minus a. With the condition that s must be greater than. This is very important formula. You can use it anytime you like. Because most of the application problems would end up with the exponential function. I just did the negative 3, so you get the feeling of how you can, how you can arrive at this. Yes.
So you like the line to signify that between 0 and that is maybe or I don't know.
Yes.
Is that just like?
You see, down the denominator, you have exponential function. You have to force that exponential function to be equal to the infinity. And stay down the denominator. If the infinity is going to be down the denominator, fraction will be 0. Otherwise, this will be jump up. So infinity will be on the top. If you get the infinity on the top, your improper integral will be divergent. and you cannot find the Laplace transform. You see, that's what I'm talking about. Always, it's up to you to make it convergent. How are we going to make it? S is free agent. So we can do whatever we like to do to get the numbers. Okay? Yes?
So, are you saying if you just substitute infinity without proposing that s plus 3 is greater than 0, it wouldn't be 0?
What are you talking about?
I mean, if you just plug in infinity, 1 over infinity.
No, just listen to me. We said you have to keep the infinity down the denominator.
It is
You can. No, don't look at this one. S is a free agent.
No, I'm
If
talking
it-
about
The only way that you can keep infinity down the denominator is that the exponent of the exponential function is positive. What is the exponent of the exponential function? B is positive. No, it's not positive.
Oh, you want to state that it's positive?
Okay, B is positive. You have S plus 3. So you must make sure that S plus 3 is positive.
Oh,
Okay, don't look at it to say, oh, it's positive. It's not. Because S is a free agent. If you have S equal to the -5, that gives you negative down denominator, which is very bad in that case. Okay, let's continue.
so you're saying, yeah.
Okay, we can come and explain it a little more for you at the end. So this is going to be exponential. Okay, as we can see, it's not going to be easy to get, through this one. So the other two that we are going to need it, I'm going to just to write it down. It's a sine and a cosine. You did have two nice problems in calculus 2. You have two integral in calculus 2 that when I teach, I do it. Integral is integral of e to the 2x, for example, cosine of the 3x. Or e to the 3x sine of the 3x. Remember the way we do it, you have to do it twice. You do it once and then get back to it. What you did in that course, you exactly find the Laplace transform of the sine function and the cosine function. So you can try it for yourself if you like, but I'm going to write the formula for you, okay? When I teach, I give them not a sine of 2x or 3x, I give them a to the x cosine of the bx. And I give them 5 points if they can find the formula, because the formula is Laplace transform. So if they need it for future. Okay, there you are. I'm not going to do it, it takes time. Okay, you can do it for yourself. So that's the second one.
This is targeted.
Yeah, the third one. Okay, the next two problems. So that was 1, 2. We need 2 more to be able to continue. How about this one? Laplace of the sine of the AT.
That's a 5-point question.
No, not for you. For calculus too. Okay, are you ready? This is it. This will be A over S squared plus A squared. That is for the sine. Very easy to memorize. Okay. The condition, I think S must be bigger than A. I don't remember. Then I check it. This is the sine. So the other one is cosine. So what's going to be the cosine? The Laplace of cosine of AT. Look at the cosine. In the case of the sine, you get the A on the top, constant. In the case of the cosine, would be S over S squared plus A squared. Make sure that you have the proper one. We can have it, you can bring it to the test, but you make sure you bring the proper one. The first one is A, the second one is S. As soon as we see the S on the top, it says the Laplace of the cosine. Okay, so that's going to be 1, 2, 3. And I need one more for the first part of the Laplace transform. So that's a 1, 2, 3, 4. That's it. The first one is Laplace 1. Now we need the next one to be able to finish the preliminaries. The next one, of course, is power function. You see, as in calculus. How about the Laplace of t squared, t to the fifth, 2 to the 6, etc. Okay, so that's going to be the one. What is, I'm going to do one of them, then you believe it when I write the other ones, okay? So let's try Laplace of t. That's the easiest one. We can make this one Laplace t. Then we can have the t squared. Now let's do this one. That's easy to find. Solution. So your function is t. Easy integration by parts give you the result. So what's going to be the Laplace of t? 0 to infinity. Okay, it's e to the st times f function. So I'm going to write down as a t, e to the negative st dt. Okay, then you change it to the limit form. B goes to positive infinity, 0 to b, t e to the negative st dt. We can find this integral by integration by part or just that tabular method. For any power of t can be done. Remember, this is it. So that was, remember, that was the sine part. That's the sine derivative integral. So the sine, we start with the positive sign. We get the t, the function e to the negative st. Okay, the second part is going to be negative. We differentiate the t would be 1. You integrate e to the negative st. It's going to be e function, but you have to divide by u prime, which is a negative s. We continue. This would be positive. Derivative of 1 would be 0. You integrate e to the negative st again, would be e to the negative st divided by negative s. That you already got the negative s here, so you make it into s squared. Okay, that's the case. And then this is the way we're going to collect the information, the integral. So what's going to be the integral from 0 to b, t e to the negative st dt is going to be equal to, the first part is going to be, this is it. The first part, you get t e to the negative st divided by negative s. Okay, minus what is 1 times. So we get e to the negative st divided by s squared. And this must be evaluated from 0 to b, and then if you need condition, you're going to impose to get it. So again, we predict the last part. You can substitute the b first, then change it. Okay, if you put the b is going to be equal to, the first one would be b e to the negative sb divided by negative s. And the second part would be e to the negative sb divided by s squared minus, if you put the 0, t0, that give you 0, minus, if you put the 0 here, that give you e to the 0, and that would be s squared. The same argument that we did for all the other ones, the limit of these two would be 0. Would you bring it down? The same thing that we did. Okay, so I can bring it down and then argue about it. So that give you b negative s e to the sb down the denominator minus e to the sb s squared. And the leftover is going to be plus 1 over s squared. because e to the 0 is 1 and you get s squared. If you take the limit with the same condition that we talked about it, sorry, I should bring this one also. This is a negative. Okay, if you take the limit when b goes to infinity, then you try to fix it so that this e to the exponential function is stay down the denominator. So in short, this goes to 0, this goes to 0. So this goes to 1 over s squared as t goes to positive infinity. Yeah, I did the same thing over there. So basically, let me finish it. So the Laplace of t would be 1 over s squared. Okay, the rest are the same. Yes,
What if the second term go to zero, that's either the negative ft over?
you bring it down, the same story. Exponential function down the denominator, infinity would be down the denominator, all of them would be zero.
So it would be 1 over s.
Yeah, as we did it for the other problems, yes. Infinity all the time. Okay, so the only condition that you have to impose is the fact that s must be positive so that you keep those exponential part down the denominator. Okay, so this is Laplace of t. You see, Laplace of t would be 1 over s squared. You can do the t squared, t cubed, etc. As you move on, that gives you the general formula that you have to memorize it. Okay, I'm going to go to the next page and give you this famous formula. And this is going to be our fifth one. So you memorize it, you can use it anytime you like. Laplace of t to the n is equal to, you see down the denominator, the power will be 1 up. So it's going to be s to the n plus 1. But on the top is going to be n factorial. Are you familiar with n factorial? 2 factorial would be 2, 3 factorial is 3 times 2, 6, 4 factorial, etc. Okay, so that would be true for n equal to the 0, 1, 2, 3, etc. So that gives you the a kind of preliminary functions that we are going to be using all the time. Okay, there are some more, but they are special. They are going to be mostly dealing with the piecewise defined function. We're going to take them, okay, one at the time. Yes. S bigger than A. In that case, because you are going to have this when we get those exponential one. Okay. So the one that I listed, you have to memorize all of them. Okay, and then we can use it. I should give you one more example. You see, these are going to be the standard. Or we can stay here and then we come back and we give you the last one. Okay, any question? So, in order to be able to find the Laplace transform of more function, it's like in calculus. You see, derivative is an operator. Derivative would have some property that we can use it, like you know, if you want to find the derivative of a sum of 2 functions. You find the derivative of the first one added to the second one. Okay, when we say something is operator from linear algebra point of view means this is a linear. When something is linear, addition goes to addition. Subtraction goes to subtraction. But if you have something like, we call it a scalar multiplication, 2 times a function. If you want to find the Laplace of a 2 times the function, would be 2 times the Laplace of the function. Because they are all integrals. When you put them together, you have it. So we are going to make it official to enable us to find the Laplace transform of more functions. In order, the application is going to be solving the differential equation at the end. In order to do the differential equation, you need all these preliminaries to be able to eventually find the solution of your differential equation, okay? So we are going to investigate various properties, but these are the easiest ones. So what is properties of Laplace transform? Enable you so far to be able. What I'm going to do is at the end of tonight, I want to be able to solve some differential equation for you. Okay, that's the target. Some easy one. Then we just go on and find more complicated. No, what we need are going to be the following. The first one, we show that the Laplace transform is an operator, the linear that I talked about. The first one is, if you want to find the Laplace transform of k times f of t, k, 2, 3, 4, 5, 6, you know, it's integral. You can pull the k out of the integral. So it's going to be equal to k times Laplace of f of t. So if you see any number like integration, put it out. Of course, k is a number, a scalar. K is a number. That's the first one. The other thing that we talk about it, you say Laplace transform is an additive operator. Additive means if you want to find the Laplace transform of a sum of two functions, f of t plus g of t. Okay, and this is it. Laplace transform of two functions. Again, it's integration. It's going to be what? Integral of the first one plus integral of the second one. So it's going to be Laplace transform of the first function plus Laplace transform of the second function. And it's the same for addition and for subtraction. Okay, so basically this shows that, if you like, this is the conclusion. Therefore, L of f of t, you can say is a linear transformation. Linear transformation or linear operator from the linear algebra point of view. You get these numbers. Let's see how we're going to use it. So you can use any of those 5 formulas that I gave you to do this type of problems. And this is your first serious problem that you're going to have in this, in this section. So what is the problem? You would like me to evaluate each Laplace transform. Laplace transform. Just using the one that we talked about it. The first one. You want to find the Laplace of this function. The function is 3t minus 5 sine of the 2t. That's it. Of course, you are not going to go to the integration formula. It takes ages to do it. Okay, so we are going to use this property that we talked about. It's like integration. Break it into parts using the linearity that you're going to have. Okay, these two properties. So it's going to be Laplace of the first one minus the Laplace of the second one. The first one, there is a 3 here. Put it out. You end up with the Laplace of t. What's the Laplace of t? You already got the formula. It's 1 over s squared. It's going to be minus 5 Laplace of sine of 2t. What is the Laplace of sine of 2t? 2 over s squared plus 4. Done. You see, this is the way we do it. Solution. The solution is distributed Laplace of 3t minus 5 sine of the 2t. It's going to be equal to, okay, you can do it right away, but I just do it in 2 steps so that you see it. It's going to be Laplace of the first one minus Laplace of the second one. Okay. Now bring the coefficient out. So that gives you 3 Laplace of t minus 5 Laplace of what? Sine of the 2t. Okay, now substitute. That's going to be 3 from the table that would be given to you. Okay, the Laplace of t is 1 over s squared minus 5 times the Laplace of the sine of the 2t. Sine is a over s squared plus a squared. So it's going to be times 2 S squared plus 4. You have to simplify it. Okay? So the algebra is going to be equal to, you get 3 over S squared here, minus 5 times 210 over S squared plus 4. You find the common denominator, which is going to be S squared times S squared plus 4. Top cross multiply 3 times S squared plus 4 minus 10 S squared. Continue. Multiply the S in here. I'm sorry, that's a 3. So that give you 3 S squared plus 12 minus 10 S squared. You don't do anything to the denominator. S squared plus 4. Combine the like terms on the top. So it's going to be 3 minus 10 would be negative 7. Negative 7 S squared plus 12 divided by S squared times S squared plus 4. That would be the Laplace of that function, okay? Laplace of 3t minus 5 sine of the 2t. This is the way we're going to operate for our function. Yes?
Wanna multiply the bottom row?
No, we don't multiply the bottom. We keep it as is. Yes, as is. So, you know, the function that we're going to use. So, you know, you can, when we write it down, we say in the natural domain. You don't have to worry about it. Because you already, on the table that we're going to use, you already put all the restrictions that you have. Okay, you can write the domain, but we don't usually write it down. We say it's going to be in the natural domain that we, you know, we impose already. Okay, I give a break. We come back and we have to do more. Okay, get a couple of more. Get used to it, and then try to change, you know, to see if we can get to the solving an differential equation. But it takes time. We need something else to go. Okay.
If you have nothing.
You like having a small iPad or? Really? Okay, that's why I think I need to get a bigger iPad.
Everybody's not gonna want to open some, almost, you're not regret it, but. I asked
I watched the video how to do both. During the, I do like a couple of times during the day. So I started one up here. like straight out the window as soon as they did. So I got here like 10 minutes early too, and I started. You do? Yeah. No, I left like half an hour before that. Well, no, I did it wrong. I don't know that I didn't do it. So it's like, right, what did you get? I got the last grade, and then like, oh, I didn't write that. Or you didn't even do it. I thought that was. Yeah, I definitely messed those up. They use stuff. When the Y is in the same or oh, those I had, and I had to. Yeah, when eggs. Yeah, exactly. I don't know, I struggle with that type. Yeah, those ones it's hard, you have to do like a separable variable thing 2 times in a row. Yeah, you have to do it fine. Why? I can't remember. No, you do it fine. I would think it's one thing you can do.
I remember 200 plays of it at this point.
I was like doing it, and then it was like, kind of nice with my ugly down. I don't know if it was
You heard it? Like, I don't want to drive. I know, it's been so fun. It hasn't been like a Canadian investor in a couple of weeks, but like, it's pretty fun. No, I think she passed out. Yeah, that was one.
Oh, I actually think I remember it was one of the, with the Y, there was one of the 4 Y. Oh, there was one that had like,
That's a good question.
yeah.
I definitely did. We're on to one.
Oh, reduction in order?
It's just kind of nice news, but, yeah.
The integral,
That's what it is.
like, oh, very. Yeah.
You wrote it, so I just.
Yeah, we had that one. That's the better, and then we had the one that. I definitely got.
I have space out there.
There's one that was like something with something about the one thousand solution.
I guess.
Oh, I did not expect to have another one.
Sure, yeah.
There was just the one for the first one and used that for the long division. Yeah. And then I ended up getting something to where. You need synthetic? Yeah, synthetic division, yeah. And I ended up getting, like, bringing it down to like where I had 1 and -2 solution, but I think it's down to 0 with the solution. Okay. And I think I was missing one solution I could not figure it out. But I
I think you sound like.
R squared.
It was right before you
was negative something,
find something.
but it was like
I don't think I.
R squared plus R squared is 4R cubed. Oh, it's R plus 2.
I wrote that down.
I remember it. It's R
Oh, wow.
squared plus 4R plus 4, something like that.
Yeah.
It must have been now. It was kind of, and I'm not gonna think so. But I was like trying to say, that was the one that we had to write the form of why we were going to solve it. I thought done with that. I think if I had to, oh, I know what I ended up doing. I ended up doing the quadratic formula. It's like I was like, really? That's. You would still get the same thing. It wasn't yeah, I got 2 complexities, but it's something like 1 plus graph 7 under 2 is my complex solution. Yeah. But my radical solution really One point grab some of it. It is 9 minus 16. And then there was divided by minus I think I was getting. I was painful, so I got -2. I ended up getting 4 AC, A was 1 C. Oh, I definitely got that one. I did wrong. I was already. One of them is nice.
Like, part of it.
These terms for the answer.
Yes.
Where's your
One of them.
I think it's 4 p.m.
Yeah.
Just something arbitrary, or do I have to?
No.
I just totally forget. I just totally forgot.
Like, I remember you.
I like lost the whole day. And I just totally missed the step where the equalize and bring it down, you have to bring the other one up, so you just have to plug in.
Oh, no, why are you going to be like that? No,
Get one for the one and then take it out. And you guys. Put down the you're gonna go on, but we're doing, we have to get the thing for you. All that stuff is going. Like, do the whole, what is it, we're in the facility to that. Part of the gravity,
I was there, I was.
it's so much better. Well, it's very loud.
Okay, I'll give you a couple of more examples. Okay. So that was number one. Number two is we talk about sine, cosine, but this is one of the problem in your book. Okay, I'll go to the next page. Okay, part two. Suppose you want to find the Laplace transform of the sine square. Okay, sine square of t. Remember, you have the Laplace transform of the sine and a cosine. And that's a sine square. Any suggestion? Sine square.
Would it just be the AS squared plus B squared square that?
No, going back to calculus 2. How are we going to find integral of sine square? Yes? See, double angle formula. So we change the double angle. Okay. So solution. Remember, the sine square of the t is 1 minus cosine of the 2t over 2. Okay, you can separate it 1/2 minus 1/2 of the cosine of the 2t. Then we can use the linearity of the Laplace transform to find it. Okay, so the Laplace of sine square of the t is the same as the Laplace of 1/2 minus 1/2 cosine of the 2t separate it. So it's going to be Laplace of the 1/2 minus Laplace of the 1/2 cosine of the 2t. You can pull out the coefficients. So this is going to be 1/2. What's the leftover? If you pull out the 1/2, what's the leftover here? 1. Very good. Minus is going to be 1/2 Laplace of cosine of the 2t. And we have the information for all of them. Laplace of 1 is 1 over s. We already talked about it. Okay, so it's going to be 1/2 1 over s. Okay, minus 1/2 Laplace of a cosine of the 80, which is 2. It's going to be s over s squared plus a squared. A is 2. That give you 4.
That 1/2, 1 over F.
1/2 1 over s. Yes, Laplace of 1 is 1 over s. We proved it. Okay, now you have to simplify it. Okay, to simplify it, just find the common denominator. You can pull out the 1/2, and then it's a 1s minus s over s squared plus 4. So it's going to be 1/2. The common denominator would be s times s squared plus 4. The top, s squared minus 4 minus s times s, which is s squared. So the s squared and s squared would cancel out. Okay, so you are going to have 1/2. On the top, you get 4 times s squared plus 4. You simplify 2 and 4. So the final answer is 2 over s times s squared plus 4. So that would be the Laplace transform of the sine square of the t. Okay, so that property of the Laplace transform to be a linear operator is very useful. Because you don't have any, if you want to do it, this type of problems directly, it would be very complicated. If you want to find the integral of e to the negative st sine square of t dt, takes times. Okay, any question? So that's one, yes, what's question? That's algebra. Yeah, common denominator. Okay. Now these are the usual practice. Now let's take one unusual function, okay? Because these are the sine, cosine. So how about this next one? This is where you have to know okay? We are going to have some tools to take care of this type of problems. But I want to check it now that you don't have those tools in case in future you need it, you're ready for it, okay? This is it. We want to find the Laplace of f of t. Check this one. Laplace of f of t when, okay, this is the function. The function is a piecewise divine function. F of t equal to, it's going to be equal to the 0 if t is between 0 and 3. And it's going to be equal to 2 if t is greater than equal to 2. In future, we have something we call it unit step function. We can do it. Let's suppose you want to do it now. Any suggestion? Yes?
It's gonna be 2 separate solutions with a given domain.
What do you mean by two separate? How are we going to separate?
You have to do a plot where the integral is from when t is 0 to 3, and then you have to do 1.
That's it. Yes, excellent. It's a piecewise defined function. You know that if you want to integrate piecewise defined function, you break it into parts. So definition only for this one. Okay. So the solution is going to be, write the definition. You can't do it, otherwise, we are going to have that formula, but not now. Yes.
How do you have two t's that are both equal to 3? Shouldn't one of them need to be greater than 11?
Yes, you are right. We drop this one. Thank you. Okay, so what is the formula now? Laplace of f of t is equal to, the general formula is 0 to infinity, e to the negative st ft dt. But the function is a piecewise defined function, so you have to break the integral. Because you have 0 to 3 and t to, okay, greater than 3. So what we do, we break it into 0 to 3. Okay, 0 to 3 e to the negative st ft dt plus 3 to infinity e to the negative st ft dt. Okay, so we are ready for it. You know, we need it, we can do it. Now bring the function. For the first part between 0 and 3, your function is 0. So this will disappear. Okay, so it's going to be equal to the 0 to 3, 0. Okay, that would be, I just write it down to give you the hint that what would happen to it. But in the second part, your function is simply 2. So that gives you 2 e to the negative st dt. Okay, so it's going to be piecewise defined function. It doesn't matter. You know, how it depends how many intervals do you have. You have to break it 0 to infinity, 0 to 3, because you have the definition for the 0 to 3, and 3 to infinity. Okay, so the first one would be up, disappear. So what you have to do is just doing the second part, which is very easy to find. Okay, so it's going to be equal to integral from 3 to infinity. Okay, 2e to the negative st dt. Those type of idea that we did, it's going to be the limit of b goes to positive infinity, and integral from 3 to infinity, 2e to the negative st dt. As we did it before, okay, exponential function. So I'm going to continue here to finish it. So it's going to be equal to what? Is the limit of b goes to positive infinity. 2 is say the same. Exponential function is going to be exponential function. But remember, you have to multiply divided by u prime. U prime derivative of the top respect to the t would be negative s. Negative s. But it's going to be evaluated from 3 to, okay, sorry, this is b. Then b goes to infinity. 3 to b. Substitute and find the limit. So we continue, is going to be equal to the limit of b goes to positive infinity. Okay, you can bring this one down and then replace it by b. So it's going to be 2 on the top, negative s e to the st down the denominator from 3 to b. If you substitute for the first part, so you are going to end up with the 2 negative s e to the bt minus, if you put the t equal to 3, that gives you 2 negative s e to the 3s. Okay, then this would go to 0. Okay, that's of course bs. That's it. So this goes to 0, and you end up with the final answer. Negative, negative, positive. So the final answer would be 2 over 3 e to the 3s. Okay, we will usually move this one up. There is a formula for it in future that you are going to see it. But for the time being, this would be the final answer. In future, we write it down in this form. That formula is e to 2/3 of the e to the negative 3s. Okay, so be ready for it when we get to the application problem. In future, there is a function 0, 1. We call it unit step function. We change everything into the unit step function, and there's a formula for it. We do it right away. Yes.
Where did you get that three from?
Yeah.
I got the, I put the, that's it. You have a 3 to be here. 3 to b, you replace the t by 3. That's S. Thank you. S. Okay, that's one. E to the negative CS over S is the formula that we're going to see in future. I just want to give you a hint. If in case there is going to be a piecewise defined function in this form, we are ready for it. Okay, but you are going to have some alternatives in future. Yes.
Why didn't you need to, impose conditions for,
The condition are natural one.
or what?
Natural.
Oh,
So, when for a couple of formula we take it, but for the rest, we say it's a natural domain. So we know that the natural domain is so that you get what? So that this integral would be convergent. Okay, that's
Is there
fine.
like a certain way to write natural domain, or we just write it out?
No, that's it. That's the usual practice. Okay, that because when you use a table that was given to you, all the natural domains are already given to you. So we don't bother to get them because eventually you are going to use this one to solve a differential equation. So there are more to, but the natural. Okay, any question? So that would be our first job. The first job is a function is given to you, then you are going to find the Laplace transform of that function. When we get to the solving the differential equation would be given to you. You assume that the solution of your equation is f of t. You take the Laplace transform of the given equation, okay? You're going to give it a formula for the y prime, y double prime, and you end up with whatever you did here. So the unknown is f of t. You end up with the Laplace of f of t. Now you have to find f of t. Okay, the other way around. So the other way around is the one that this is an operator, this is a function. So each function would have one inverse. So in the case of the differential equation, you have to find the inverse of Laplace transform. You have to find a function for which the Laplace transform is already given to you. So you have to practice that one. Okay, so what is the inverse of the Laplace transform? So what we're going to do is that this would be given to you, then you have to compare with the table that you have in order to find out what function would satisfy this, okay? So in fact, f of s would be given to you. Then f of t is the missing part. Then, if it's going to be a kind of exponential function or the sine and the cosine, you are going to have it. So I write the definition. It's all algebra. You need a very good partial fractions that you did again in calculus 2. Okay, we did quite a lot. We get back to those functions, and you got to be very patient. Some of them takes time to be able to do it. Okay, but it can be done. So that is we are done so far with section 7.1. So that would be 7.2, the inverse of the Laplace transform. Okay, let's see what's going to be the inverse. So if you like, we go to the 7.2, or just part of this. What is the inverse of a Laplace transform, or the inverse Laplace transform? Okay, what is inverse? Inverse Laplace transform. Like any other function, you can define an inverse for the given function. This is it. Okay, there you are. This is it. Suppose the Laplace transform of the function is given to you, okay? Suppose a Laplace of f of t. Remember, this is equal to what? It's going to be equal to a function of s. So suppose L of f of t is given to, it's going to be equal to the f of s is given. Is given. Then the inverse. The inverse. Laplace transform. Laplace transform. We want to get back, okay? Switch is going to be denoted by denoted by Laplace inverse. Is the notation -1? Laplace inverse of what? Of f of s. And is defined by? Is going to be defined by, that's it, Laplace of f of t is equal to the f of s if and only if inverse, Laplace inverse of f of s is equal to the f of t. So basically, the Laplace of a function is given to you, you want to find the function. Okay, it's like, the derivative of the function is given to you, you want to find the function. So the opposite operation that you use is integration. You get these numbers true. Okay, so you have to compare it with those 5 formulas that we give you. Okay, you have to know those. Okay, the Laplace of power of the t. Remember, Laplace of t to the n factorial s to the n plus 1. Laplace of exponential function, Laplace of e to the at 1 over s minus a, Laplace of a sine or a cosine. Okay, so give you this possibility. This is your, when you want to solve a differential equation by the Laplace transform, this is the final part. The first part is we do some operation, we simplify everything, we arrive at this one. Then we do the inverse. So I give you some famous one, some algebraic methods that we need, so that you'll be ready for it when the actual one would be given to you. Okay, so there you are. Let's practice. Example. Example are going to be, we want to find. Okay, find the given inverse transform, inverse transform or inverse Laplace transform. You get quite a lot. You better quickly check check your assignment, start working on these. Okay, that would be very, very useful. So the most popular one are going to be the following. The first one. The first one is, how about Laplace inverse of 1 over s squared plus 64. You see, you check to see if it's going to be familiar or similar to which of those formulas. The bottom one is the sum of 2 perfect squares. On the top is a constant. If on the top is a constant, this must be sine. If the top is s, this must be cosine. Easy to find. Okay, the top is a constant, so it must be a over s squared plus a squared. But you check to see if it's ready. You see in this problem, s squared plus 64. A squared is 64. So we want the a on the top. It's like integration. I want the a, I'm going to create it. Remember, I divide, I multiply. So this is the way we're going to do it. Solution. So we say, I would like to find the Laplace inverse of 1 over s squared plus 64. Okay, I just remind you, you take your a squared with the 64, so your a is 8. So what I do is, I divide the outside by 8, then I multiply the inside by 8. That's it. Remember, Laplace inverse or Laplace, they are all operators. You can switch the numbers. It's integral. Okay, now we are ready for it. The inside one is what? Is going to be 1/8. It's going to be the sine. The sine of what? 8t. And we're done. Okay, so if you want to find the function whose Laplace transform is 1 over s squared plus 64, that function is 1 over 8 sine of 8. When it's going to be a differential equation, this would be the solution of your equation. Remember, this is f of t. This result that you got is, you don't have to write it, but this is your f of t. get the numbers. That's a type 1. So if there is a constant on the top, it's a sign. If the constant is missing, nicely you can, okay, you can create it. You get these numbers. That is type 1. Any question? Then for type 2? Type 2. Type 2, something like, how about Laplace inverse of 10 times s divided by s squared plus 16. You see, 10 is not important. We can put it out. So the top you get s, down the bottom, sum of 2 perfect squares. You know that would be cosine. Okay, if it's get the constant on the top, it's a sine. If you get an s on the top, it's a cosine. So again, you have to pull out that number, that extra number, 10s, s squared plus 16. You pull out the 10, Laplace inverse, s squared plus 16. A squared is 16, a is 4. Just remind you, a squared is 16, so a is 4, and we know that this is going to be cosine. So it's going to be 10 cosine of 40, and do that. Okay, so f of t, if you like, is equal to the 10 cosine of the 40. That's 2 very popular cases. Any question? So, ready for the next one? What's going to be the next one? Part 3. How about this? Laplace inverse of 3s plus 5 divided by s squared plus 7. Yes, that's it. So what we do, we are going to break it. Okay, we break it. If you get the s on the top, it's cosine. If you get the number on the top, it's a sine. You have a combination of both of them. Very good. Okay, so break it. Solution. Laplace inverse of 3s plus 5 over s squared plus 7 is equal to what? I just break it so that you can see it, but you can do it right away. It's a 3s, s squared plus 7, like fraction, plus 5, s squared plus 7. Now it's going to be Laplace inverse of the first one plus the second one. So it's equal to the Laplace inverse. Okay, of what? 3s, no, s squared plus 7 plus Laplace inverse of 5 s squared plus 7. Okay. If you pull out the 3 out, the left over is going to be cosine. So you can do it right away, but I just do it step by step. Laplace inverse of s squared plus 7. This is going to be 5. Laplace inverse of 1 over s squared plus 7. Now we are going to operate. The first one is s over s squared plus 7, so it's a cosine. It's red. A squared is 7, so a would be radical sign, root 7. Okay, it's going to be 3 cosine. Okay, the cosine of root 7 of t. That's the first one. Second one. What do you need for second one? You need root 7. So you can create the root 7 on the top, or guess, if you feel comfortable, you can do it right away. So what you do is, you are going to divide the outside by root 7, and then you multiply the inside by root 7 to create the a on the top. Okay, now we are ready. The first one is already 3. Cosine of the root 7 of t. This would be 5 over root 7, not the same. Sine of, okay, root 7 of t, the final answer. Okay, so these are going to be happen, as soon as you get to the solving a differential equation, you will see all of them. You may see a couple of them in, okay, you may see a couple of them in solving one differential equation. Okay, any question? Yes, what's good? Why added? Function.
Oh, okay, we added.
You must have a function. You see, remember it's AT, sine AT, cosine AT.
Why is it 5 over root 7 again?
You see, in the case of the sine, the formula is A over S squared plus A squared. So you need the A on the top. A is radical 7. You don't have it? You divide and multiply, you see? You can cancel it out. It's like integration. In integration, you do your substitution. This is the way you do it. But over here is a constant. We can go around and take care of it. Okay, ready for the next one? So what's going to be the next one? The next one, this problem can be done by a different formula in future, but there is a method that we want to warn you, make sure you know it. So this is case 4. What's going to be case 4? Case 4, we want to find the Laplace inverse of this function. Laplace inverse of, you see the top would be S, the bottom one would be S squared plus 2S minus 3. Remember the possibility that you have. Any suggestion? Down to the denominator, we get a quadratic expression. Yes?
Back to the bottom.
That's it. Very good. Factor the bottom, then the partial fractions, break it into the 2 different functions, and do the job. Okay? It's like, like integration. It is integrations. Okay? So there you are. We have to work on this function first. So let's pull it out, do the algebra, then go back. So this is going to be S. Common, then factor it. Give us the numbers. S plus 3, S minus 1. You have to linear factor, break it. Partial fractions. It's going to be S plus 3 plus S minus 1. On the top, A, B, or I'll go with the A1 and A2. Find the common denominator to find these. So it's going to be equal to, the denominator would be X plus 3, S minus 1. The top, cross multiply, is A1 times S minus 1 plus A2 times S plus 3. Get the top to be equal to each other and work to get the A1 and the A2. So what's the top? A1 times S minus 1 plus A2 times S plus 3 equal to S. Pick those nice numbers. What's a nice number? 1. That's it. S equal to 1. The first one would be 0. The second one would be A2, 1 plus 3. Remember, on both sides of the equation. So that gives you 4A2 equal to 1. So A2 would be a quarter. That's A2. Okay, go back, repeat it for the second number. The second choice was -3. S equal to the -3. So you have to apply to the first part, A1, -3 minus 1. The second part would be 0, equal to the S, which is a -3. -3 minus 1 would be -4. -4 A1 equal to the -3. So A1 would be 3/4. So we go back, you break it into two easy integral, and you upgrade it. Okay, going back, rewrite it. It's going to be Laplace inverse of A1, 3/4. It's a 3/4 S plus 3. A2 is a quarter S minus 1. You know that S minus A is exponential function. So you don't need those coefficients, so you can put them out. So it's going to be 3/4 Laplace inverse of 1 over S plus 3 plus a quarter Laplace inverse of 1 over S minus 1. So I'm going to use this formula. Remember, the Laplace of e to the at is 1 over S minus a. That's the formula. If you compare it, so the first one would be 3/4 e to the a is a negative 3t, plus a quarter e to the a is positive 1 t. So that gives you the final answer. Okay. We're going to have various differential equations that will end up with this one. Okay, and then that will be your f of t. Okay, any question? So this can be in various formats. So I should give you another one. Any question? So it's all algebra really. The main one is you already done. So we put this together to eventually be able to find that differential equation. Okay, so I should give you one more. This can be done again in future by an easier formula, but you are going to have it. So let's see. It's going to be 1 over S squared times S squared plus 4. So this one. Again, you have to use the partial fraction.
But this time it's not only A1 and B1.
Yes,
We have to add BX plus C.
yes, yes. But you can do it, write down in easier form. You get these numbers. Because when you do the integration, your denominator would be what? It's going to be 1 over S. 1 over S squared. And then you get 1 over S squared plus 4. But for this type of problem, if you have 1 over S squared, you'll be fine. You can do it. Remember, this is the formula that we have. The Laplace of t to the n is what? Is n factorial over S to the n plus 1. So one easy way to do it is just break it in this form. Okay, if you want to have something quick. So this is it. You have S squared plus 4, a shortcut. The shortcut is I break it into the S squared, then I break it to the S squared plus 4. You see, over here, I have only a constant. So I should arrange it so that this S squared would disappear. So what I do, I put the 1 and -1 here. So if I put the 1 and -1, what's going to be the result? This would be 1 times S squared plus 4 minus S squared. What's going to be the result?
4.
S squared plus 4 minus S squared. That would be 4. But you need 1. So what you need to do is divide by 4. You see? That gives you the partial fractions right away. So if you get a chance, just apply it. You get these numbers. Okay, so since you need a constant, so you should take care of the S squares. So you need a positive S squared to cancel it out. So I put the 1 and -1 first, do it. If you get a 1 here, you're done. If you get any other number, go back. and change it. Okay, so this is another point that you're going to use. Now there you are. So the Laplace transform of the given one would be changed into this one. So we get a quarter over s squared plus, it's a negative quarter, s squared plus 4, break it, and you bring these numbers out. Now you know what we do is a quarter Laplace inverse of 1 over s squared minus a quarter Laplace inverse of 1 over s squared plus 4. Okay. Now let's see if you can do it, or if you need something else, take care of it. The first one. The first one, you compare it here. Okay, if you compare it, this is s squared. So n must be 1. Okay, you get a 1. So this is nothing to worry about the first one. So that would be t only. Okay, Laplace of t is 1 over s squared. It's done. Yes.
Second one would be sine.
The second would be sine, but you need something else before going to read.
Plus 2 on the top.
You need a 2 on the top. Okay, because s squared plus 4, a squared is 4. So we create a 2, a quarter. You divide by 2, and then you multiply by 2. You see, it's always you need to do this type of operation for the sine. So what's the final answer? A quarter t, that give you minus 1/8, and this is going to be what? Sine of the 2t. So that would be your function. And then you're done. Okay, so you need this experience to be able, when we get to differential equation, this is 50% of your problem. You simplify it, you get to this one. Okay, then you do it. Yes. Yes, you see the partial fraction, the number, you have the s squared and the s squared plus 4.
I was just thinking about what's in the red, what's
Yeah, I'm explaining. Okay, the top is a constant. Since the top is a constant, this can be done quickly. So this means you should arrange it so that this s squared should be disappeared. It's going to be disappear if you get s squared minus s squared. So that's what I did. I put the 1 and negative 1 first. If it's going to be 1, negative 1, when you do the job, it's going to be what? Cross multiply. 1 times s squared plus 4 minus s squared. S squared and s squared cancel out, you get a 4. But you need the 1. So what you have to do? You have to go back and divide whatever you pick, divided by 4. So if you do it now, you see, this is going to be negative quarter of s squared. This is going to be positive quarter of s squared. They will cancel out. The constant term would be a quarter times 4, 1. Okay, these are going to be your advantages you're going to have. You know, you save time when you do this type of operation. And we did this type of things in calculus too. When you did the power series, okay, the function was given to you. You would like to find the power series of the given function. So this is where we get it. Yes.
Think about 1/4p. What does that have to do with either the n equals n factorial over f?
Just compare it together. So what you have? 1 over s squared. Go to this formula. For what value of n, you get s squared here. 1. Okay, so that 1 plus 1. So your solution must be t to the first power.
Oh.
Which is good. Okay, you compare them together. Okay, you will get. Sometimes you may need to create that factorial. But in this case, 1 factorial is 1. You are lucky. Okay, if it's going to be any other power, you have to do. Okay, so this is going to be the 1. So I should give you 1 more to see how patient you are. Okay, and let's see. This is one of the problem in your book. I just wanted to see, okay, just give you something that you got to be patient to. It's not difficult, but just give you something that you know you should expect it. Okay, so number 6. So after tonight, we are going to be ready for solving the differential equation, of course. But we need this. Okay, how about this one? Let's see. What is Laplace inverse of this function? 1 over s minus 1 times s plus 2 times s minus 4. This is one of the problems in your book. You know what to do. You know it's a product of the linear factors. So you break those linear factors and you do the algebra. And at the end, it's going to be a couple of exponential functions. Okay? So let's break this one. There's no shortcut for this. I know it can be done. So that's it. S minus 1, S plus 2, S minus 4. So you get what? S minus 1 on the top A1, S plus 2 on the top A2, S minus 4 on the top A3. Find the common denominator, let the top equal to each other. You have 3 nice numbers. So you'll be able to find it. Okay, what's the common denominator? Common denominator would be S minus 1 times S plus 2 times S minus 4. The top, A1. You drop the S minus 1, the other factors. So it's going to be S plus 2 times S minus 1. That's the first one. Plus A2. You drop S plus 2 from your common denominator, you multiply by the leftover. Plus A3. You drop S minus 4 from your common denominator and you multiply by the leftover. That's it. You let the top to be equal to the 1. And then you pick those 3 choices, 3 numbers to find A1, A2, and A3. Okay, so I have to rewrite that. It's A1 times, okay, A1 times S plus 2 times S minus 4. A2 times S minus 1, S minus 4, plus A3 times S minus 1, S plus 2, equal to 1. That's a kind of auxiliary equation, okay? 3 numbers. What's the first one? Easy one. 1. S equal to 1. You can substitute here, so that give you A1 times 1 plus 2 times 1 minus 4. Everything else would be 0. Equal to 1. It's going to be 0 because you have S minus 1 and S minus 1 here. 1 plus 2 would be 3. This would be 3. This would be negative 3. So we get the negative 9. A1 equal to 1. So A1 would be negative 1, 9. That would be, okay. So that was S plus 2. That's a 3. I didn't make any mistakes. Okay. Oh, okay. So that would be 1, 9. That's the first one. Okay. Go back. Second number. S equal to negative 2. For the negative 2, this would be 0. You have to substitute here. It will be A2 times negative 2 minus 1 times negative 2 minus 4. The other one would be 0 equal to 1. So that gives you a negative 3, and this would be a negative 6, and negative 3 times negative 6, 18. 18, A2 equal to 1, so A2 would be 1 over 18. So that's 18, A2. Okay, the third number is 4. S equal to 4. Again, the first one would be 0 because of the S minus 4. The second one would be 0. So we get to the third one, A3. 4 minus 1 times 4 plus 2 equal to 1. So that give you 3. That give you 6. 6 times 3, 18. So A3 would be 1 over 18. Okay, now go back, substitute, you get 3 exponential function. Okay, so the result is going to be this one, Laplace inverse of A1, negative 1 over 9. Negative 1, 9, S minus 1. A2, 1 over 18, S plus 2. A3, 1 over 18, okay, S minus 1. Break it, bring these numbers out. Negative 1, 9. Laplace inverse, again, you can, substitute right away. S minus 1 plus 1 over 18. Laplace inverse of 1 over S plus 2. Okay, plus 1 over 18. Laplace inverse of 1 over S minus 1. They are all E function. So the first one, negative 1, 9, e to the t. The second one, 1 over 18, e to the negative 2t. And the last one, e to the 40. So that gives you the final answer. This is the first group of the function you're going to have. And these are, the functions are uniform, okay? And there is no piecewise defined function around this one. There's going to be another group. We talk about it later. Okay, it's going to be more technical.